As we finish up our discussion of right triangle trigonometry definitions, and we're preparing to begin talking about the unit circle, which is used extensively within trigonometry as well as calculus, I want to review two of the special right triangles that you may have discussed in a geometry class somewhere in your past. And one of those is a 45-45-90 triangle, and the other is a 30-60-90 triangle. So we're going to start with the 45-45-90 triangle. I want to show you kind of this relationship. So what I have drawn here is a square, and hopefully you know that on a square, all four sides have the same length, okay, first off. Okay, so each side is the same length, and we don't know what that length is, so we're going to call it x. So each side has a length of x units. We also know that each of the angles in the corners for the square are 90 degrees. So we're going to begin by drawing a diagonal from one corner to the opposite corner, which bisects the angle. So if the angle is originally 90 degrees and it's bisected or divided in half equally, that gives us a 45-degree angle and a 45-degree angle. So that you ultimately have a 45, 45, 90 triangle. So, and I'm going to kind of outline it here with the green. Okay, you actually have two of them, but we're going to use this lower one. Okay, so now we have a 45, 45, 90 triangle. And we know that each leg has a length of x. What we do not know is the hypotenuse, which is represented by the diagonal. So this is our unknown. I'm going to use D for diagonal. We don't know what that equals. But if we use Pythagorean Theorem, we can develop a relationship between the legs and the diagonal. So if I apply Pythagorean Theorem, which we have leg squared plus leg squared equals the diagonal squared. Okay, so 1x squared plus 1x squared gives me 2x squared, which equals the diagonal squared. And I'm trying to solve for the diagonal squared. Okay, so then to undo the square we take the square root. And again, because we're representing a distance, we can ignore the negative, so we're focusing on the positive. So we have the diagonal equals, and then I can simplify this radical, and we should always do that. We have a perfect root, so we have x times the square root of 2. So from this, we now know the diagonal is the square root of 2 times x. So what we know, we can kind of develop a formula here, is that x equals the leg of a 45, 45, 90 triangle. And our hypotenuse would be the leg length at x times the square root of 2. So ultimately, the hypotenuse of a 45, 45, 90 triangle is the square root of 2 times the leg, or times the side of the triangle. And that gives us our hypotenuse. Then if we think about our trig relationships, knowing that this hypotenuse is x times the square root of 2, and you think about your trigonometric relationships. And it doesn't really matter which one of the angles we decide to focus on because they're both 45, but let's say we focus on this angle here so that you have opposite and adjacent, and of course, the hypotenuse. All right. So then if I think about, okay, what would be the sine of 45 degrees, which is the opposite over the hypotenuse, we would have x over x times the square root of 2. Well, if we simplify that fraction as we should, okay, well, I notice that I have an x in the numerator and an x in the denominator. Now, there's still a placeholder of 1 in the numerator, so we have 1 over the square root of 2. Now, we never leave a radical in the denominator. We use the process called rationalizing the denominator. So I'm going to multiply the numerator and the denominator by the square root of 2 so that I end up with square root of 2 over 2. So the sine of 45-degree angle is always going to be square root 2 over 2, regardless of the length of the sides because of the relationship between that. And that's one of the basic trig values that you might see used a lot. So you may want to commit that one to memory. If we think about the cosine of 45 degrees, which is adjacent over the hypotenuse, okay, we would still have x over x over square root of 2. And again, if I go through that process of simplifying, okay, I have an x in the numerator and an x in the denominator, placeholder of 1. So I have 1 over square root of 2, which is square root 2 times square root 2 to rationalize that denominator. You never leave a radical in the denominator. And again, we get square root 2 over 2. So the cosine of 45 degrees is also always going to be square root 2 over 2, again, regardless of the size of the triangle. And then finally, if we take a look at the tangent, we have the tangent of 45 degrees, which is the opposite over the adjacent. We would have x divided by x, and I hope you realize that that would simplify to 1. Any number divided by itself is going to be 1. So the tangent of 45 degrees is always 1. So we can develop these special relationships stemming from the special relationship of that right triangle. So again, these are some very commonly used trig values for 45 degrees. Also remember that 45 degrees corresponds to pi fourths, okay? And so these would also apply to pi fourths. The sine of pi fourths would still be square root 2 over 2. Cosine of pi fourths would be square root 2 over 2. And the tangent of pi fourths would be 1. Depends on whether you look at it from degrees or radians. So that's a special relationship. And again, I would encourage you to commit those to memory, but also think about or remember this special relationship here. Because if you ever forget, you can develop it if you remember this relationship, which you could develop through the use of Pythagorean theorem.